Tudor here at the Center for Academic Success at Pierce College, and today we're going to go over arguably one of the most important and practical concepts in mathematics, and it's known as the average rate of change. So let's start off by looking at two real-world examples, and from there we'll build upon an idea that wraps around a conceptualized formula. All right, so let's suppose it's 6 a.m., you're on the 405 freeway, and you need to get to LAX within 7 a.m. in order for you to make it to your flight on time. So let's go ahead, I'm going to go ahead and draw a diagram for that, a sketch of it. So this is your starting point. You're driving on the 405 freeway, so this is the 405. And you want to get to LAX within 7 a.m. And you're starting at 6 a.m. Let's also suppose that you need to drive 60 miles, that from where you start to LAX is 60 miles as well. So the natural question here is, how fast do I need to be driving on average in order to get from where I start to LAX on time? Just thinking about it for like a minute or two, one can deduce that we need to be driving 60 miles in 1 hour. So in other words, we need to be driving 60 miles per hour in order to make it to our flight on time. So this 60 miles per hour right here is what is known as the average rate of change. So in other words, it is an average rate of change of the distance traveled with respect to time within the 1 hour driving from the starting point to LAX. So we could think of the speed of the vehicle, right? Because a speed of our vehicle, if you think about it, we're driving 60 miles per hour as a measurement of the amount of distance traveled within a given time lapse. So if I were to rewrite it like this, 60, because we could do that, 60 miles per hour, here we can see here we change the measurement of the distance is 60 miles within 1 hour of time passing by. But unfortunately, we live here in California, Southern California, and at 6 a.m., 7 a.m., we have traffic jams and everything. So realistically, I don't think we're going to make it within an hour, right? From 6 a.m. to 7 a.m., 60 miles in between, we're not going to make it. Might as well just sleep in, right? That's what I'll do. So in the previous example, we went over a freeway average rate of change of distance over time problem, where we concluded that we need to be traveling on average 60 miles per hour, right? But like I said, realistically, we won't be able to drive that because there's always traffic jams on the 405 freeway. There's people getting into accidents, and that has to do with our population here in Los Angeles. Speaking of population, another very important application to the average rate of change is population growth. So let's take our county, right? The county of LA as an example. Records indicate that the LA County population in 1990 is roughly 8.9 million. I'm just gonna go ahead and just write 8.9. 5 years later, the population in LA, so 5 years later, so that's from 1990 to 1995, it went from 8.9 to 9.1 million. So I'm gonna go ahead and write the million because it could get a bit confusing. Okay, great. And lastly, as I mentioned earlier, today in 2015, all those traffic jams and all those car accidents are caused by the huge population that we have today, which is actually at a whopping 10.1 million. So for our purposes, we are going to assume that the population growth here in LA is constant. In other words, it grows at a linear fashion. So let's take this example that I have here. So from 1990 to 1995, that's 5 years, right? The population grew from 8.9 to 9.1. That's a 0.2 million increase, right, of people. But I really don't like points, so I'm going to go ahead and change 0.2 million to 200,000, right? Because that's the same thing. So just kind of thinking about it for a minute or two, from 1990 to 1995, in 5 years, our population growth was 200,000. So you can say, another way of saying that is our average rate of change of of people with respect to the amount of time that passed by is 200,000 over 5, right? Because that was our population growth over the 5-year span from 1990 to 1995. So if we go ahead and simplify this, that's really about a 40,000, the average rate of change of people with respect to time is really 40,000 people per year, per 1 year. So the 40,000 here that we just deduced is exactly the idea that we're trying to grasp. The 40,000 here is a measurement of the average amount of people that the LA County increased by per year from 1990 to 1995. In other words, it is the average rate of change of the population with respect to time. And the interpretation should be as such, that the population of the LA County grew at an average rate of 40,000 people per year between the years of 1990 and 1995. Alright, so let's now look at the average amount of people that the LA County increased by per year from 1995 to 2015. So here we are given that in 1995 the population is 9.1 million, and in 2015 the population is 10.1 million. So from 9.1 million to 10.1 million, that was a 1 million people increase, right? And that was in a 20-year span, right? Because from 1995 to 2015, that's 20 years. So in other words, we can say that your average rate of change of people with respect to time, let's not forget the units, people, years, is really, if you were to use your calculators to simplify this, you'll see that you'll get 50,000 people per year. So again, we can conclude that the population of the LA County grew at a rate of 50,000 people per year from the years of 1995 to 2015. So notice that in the last two examples, we could have actually taken the difference between the distance, or in this case, right, the one I have on the board here, the population, and divide them by the difference of their corresponding years that it occurred. So let me go ahead and write that out for you. So let's take the case from 1995 to 2015. So in 2015 we said there was 10.1 million people. I'm going to go ahead and just exclude the units for now. 10.1. If we take the difference between the populations and divide that by the difference of the years, we will see that we get, I'm going to go ahead and write that here, we get 1 million over 20 years, which is the same thing that we got over there. So this conceptualized formula, if you want to give it a name, gives us the average rate of change, in this case the average rate of change of your population with respect to time. If we allow t to represent time in years and p to represent population in millions, we can actually express our conceptualized formula like so. You could say change in p divided by change in t. Observing that the population of LA, depending on what year we were in, we can think of the population of the LA County, call it P, as being dependent of the year. And as a result, we can expand our definition of the rate of change to be a measurement of how much one variable, typically being the dependent variable, changes with respect to another variable, and that variable typically being the independent variable. In this case, we are measuring how much the population, the dependent variable, is changing on average with respect to the change of the years we are measuring.